Okay, so I will try to explain to you what TrueBit is all about, why we need it, and what it can be used for. To start, I would like to talk about the topic of scalability. This is a chart of Bitcoin transactions per day. And it starts in January 2009, and this is basically now. It's a linear scale, and you can already see that, yes, so it's growing. Perhaps not so much in the last months, but yeah. And it's a similar chart for Ethereum. This is, transactions per day also, starting in July, August 2015 until now. And I would also say it's kind of growing. And yes, so the question is, so most of you might have heard that blockchains do not scale currently, and this is one of the main debates in the Bitcoin community. But what does it mean? What does to scale mean? To put it simply, something scales if it performs equally well as it grows. And currently for Bitcoin, there is empiric evidence that this is not the case, because it gained more and more popularity over time, and now it's harder and harder to get transactions accepted, and they also get more expensive. And of course, this problem exists in exactly the same way for Ethereum, perhaps even worse, since transactions can be more complicated. But currently, Ethereum did not hit this limit yet. And what is the reason that blockchains don't scale? The simple answer to that is that every full node has to process every single transaction, or verify every single transaction. And of course, this does not really work well, because you have the fixed block time, the time between two blocks. And in this time, if the system grows, which means it has more and more transactions, then every node would have to process more and more transactions in the same time interval. In scalable database systems, for example, you have the property that if the usage increases of something, of that database system, then you can just add more servers and it will balance that out. So if you add more nodes, then you can cope with higher demand. And that is not possible with blockchains because of this property that every full node has to process every single block. And of course we have this property because of trust. If we distribute transactions just across some nodes, then those nodes might be able to cheat, because not all other nodes verify the transactions. And so, as I already said, scalability is also exactly the same problem in Ethereum. And the difference between Ethereum and Bitcoin is that we were very well aware of that from the very start. Which does not mean that we knew the solution for the very start, or that we had some way to already prepare for scalability, but we at least knew that we will have to do at least one hard fork to cope with the scalability problem. And there are at least 3 proposals how to scale the Ethereum blockchain. And the first one is the Casper research program. So Casper is not just about proof of stake, but also about trying to scale the blockchain. And the idea in Casper is that you use a concept called sharding. That's more or less the same concept that is also used for these scalable distributed databases. There the idea is that you just send transactions to just certain nodes for verifying, but Casper makes it secure again by rotating these verifiers in regular intervals. Then there is Raiden, which is the Ethereum analogy of the Lightning Network, which is the Bitcoin Lightning Network. And there the idea is that you can scale transactions by grouping them in a certain way. You move them off chain, so you don't process them in the blockchain, but you process them in a different network. And then at the end, you group multiple transactions into a single transaction and just put that transaction on the blockchain in very, very simple words. So you can get more transactions in quotes into a single actual transaction on the blockchain, and that's how it scales. TrueBit is the third way, and there the idea is to scale computations. I will explain a bit more later what that actually means. And the way to scale it is using interactive verification, that we will also go into detail later on that. And also a nice thing to note is that only Casper requires an actual fork, because the other two ways to scale can be directly implemented on the smart contract mechanism. Okay, why do we need to scale computation? Ethereum has smart contracts, which means computations running on the blockchain, but they are limited in complexity, limited in resource usage, because of the fact that every full node has to process every transaction. And with TrueBit, you can get smart contracts which do not have a gas limit, essentially. They can be written in any programming language. The reason behind that is, so if you don't have a gas limit, you can just take a program written in Python and then just put the Python interpreter on the blockchain and run the Python program through that. Ethereum smart contracts can be driven by neural networks, so that we can have artificial intelligence on the blockchain. And you can even have file system access in smart contracts, which means you have a smart contract, then it accesses a terabytes big file and reads a single chunk in there, or even computes a big sum over all the entries in this gigantic file. Of course, these smart contracts will not run directly on the blockchain. We know it doesn't scale, but the trust promise will be the same as if they would run on the blockchain. So this was a bit abstract. Some more specific practical examples. With TrueBit, you can link multiple blockchains. So there's this Dogecoin Ethereum bridge project, which tries to create a bridge not only from Dogecoin to Ethereum, but also from Ethereum to Dogecoin. And the idea is that you can take Dogecoin and move it to the Ethereum blockchain, where it will be an independent token. You can move it around as a token there, and then also move it back, destroying the token and releasing or generating new Doge on Dogecoin. For that, you basically need a light client for the other network for one network in the other network, and the light client for Dogecoin running on Ethereum will, as I said, so if you don't have a gas limit, you can just implement anything and verify the full Dogecoin blockchain on Ethereum. Another project is so Golem. Golem is a project to pay for other people to do your computations, and their white paper mentions TrueBit to actually verify that these computations were done correctly. And another example is LivePeer. They want to create a video streaming platform where people are paid to encode the videos, and they want to use TrueBit to verify that the encoding was done correctly. Okay, another very nice property of TrueBit I want to mention is that it has so-called unanimous consensus. This means that, okay, perhaps I should first explain the general framework. So TrueBit works in a way where you have a computation task, you have a program to run, someone runs the program off-chain and puts the result on-chain. And then people can rerun the same computation and check that it was done correctly if they want. And the idea, so this is similar to a blockchain where you have multiple miners who process all transactions and then verify each other. And on a blockchain, if you have a disagreement there, then you get a fork. And if you can convince over 50% of the hash power that your version is the correct one, then you basically convince the whole network. Not exactly like that, but roughly. And for TrueBit it's different because you have to convince every single person. So as long as there is a single honest person who checks the computation and posts on the blockchain that he or she disagrees, and the person is actually right, then it will not go through. So the person will get their result. Yeah.
So basically, there's only one transaction per questionable execution. Basically, not on every computation I have to submit a transaction to the result, but only if there's one question and I want to debate it, basically.
I didn't understand the question, sorry.
I run a transaction and I'm saying that was done wrong, someone was cheating, then I submit a transaction. But I don't submit a transaction if everything runs fine and everybody agrees. Right?
Yes, yes.
So only in the case of actually cheating.
Yeah. Okay. And another question?
You probably get this, how is that done? Is that through sampling or how is that?
We'll get there. Yeah, so some of you have been here in an earlier talk about the same topic, and this first line was already in the first talk, but the second line is actually new. So some months ago we said, okay, a single honest verifier suffices so that nobody can cheat, but it turned out that this single honest verifier is not always there, but we added an economic incentive mechanism to actually ensure that this single honest person is also always there. And so there are other projects which do similar things, like Golem, iExec, and Solemn, but the difference to those projects is that they focus mainly on performing the computations or outsourcing the computations, but not on the fact that they are done correctly. And TrueBit, on the other hand, is focusing mainly on correctness and not on reducing the costs or something like that. So TrueBit is really about scaling up what can be done inside a single transaction, if you know. Yeah.
So if you don't have gas limit, how do you solve the halting problem? How do you know when a program?
Okay, so it's Ethereum smart contracts, but with a very much higher gas limit.
Oh,
You're right. So TrueBit has some concept of gas, but it's much more relaxed than Ethereum. Okay, so yes, this was the non-technical part. Just to scare everyone here. Yeah, I hope it's still all be understandable. So how do we do that? Yeah, as we already said, the main problem why we cannot scale computation is because everyone has to compute everything. So the solution is obviously build a system where not everyone has to compute everything. So I have a computational task posted on the blockchain, and 2 or 3 people take it on and perform the computation, and then post the result on the blockchain. And the main point here is not we just take the majority answer, but the main point is if we have any disagreement here, then these people go to court, and court here means blockchain. So we have the smart contract judge, which who finds out without error who gave the wrong answer. And yeah, again, the simple solution here would be that the smart contract just reruns the full computation, but that again doesn't scale. So the checking who was in error has to be magnitudes faster than actually running the computation. Okay, and how do we do that? We use a concept called the verification game. And the key term is here is not sampling, but binary search, and we'll see how that works in a minute. So a computation in a sane computation model always consists of some kind of steps. So we have a computation which starts at step 1 and ends at step 1 million. And every single step is quite small, easy to follow. And we have a proposer with an input, a challenger with the same input, but at the end they come up with 2 different outputs. That's their disagreement. And what they do is they rerun the whole computation while taking a snapshot of memory at every single step, computing a Merkle tree of that snapshot, and storing the Merkle root. They do not submit the Merkle root, they do not submit all the Merkle roots to the blockchain right away, but they store them. And this means, yeah, the Merkle root at the beginning will be the same because they started in the same, in a very fixed setting, and it will be different in the end because their memory content, their output is different. And then the smart contract, the judge, will come and say, will take the step in the middle here, and ask them for the Merkle root of their state at that point in time, and they might give the same answer. This means that at some point here in this second half, there has to be a single step, at least one single step, where we go from agreement to disagreement. So both parties were in agreement here, but they are in a disagreement here. So at some point along the line here, they have to move from agreement to disagreement. And that's just the point we search using binary. We try to find using binary search. So the smart contract asks for the center position here, and the parties again reply. Here they gave a different reply, so we continue the search in this area. This goes on, and at some point, because the size of this time interval always halves, at some point we will reach a situation where we have one step where both parties are in agreement, and the next step where the parties are in disagreement. And the good thing about that is that a smart contract can just start with the situation here in this step and just recompute a single step and check which is the correct result. Because a single step is easy to compute. We have some computational power on the blockchain, but it's very limited, and yeah, a single step easily fits in this limit. Okay, so this takes 20 rounds, which is quite long, I would say. I mean, it's still tiny compared to 1 million steps. That's what I said. It has to be magnitudes faster on chain than actually running the full computation. But still, yeah, the good news is that these 20 rounds can be further reduced. And furthermore, the cheater is found with certainty. There's no way to get around that. And but because of that, if you try to cheat, you already know you will lose in that game if someone watches. Then why would you want to play the game? So why would you want to cheat? So as long as you know that someone watches, you will probably not cheat, which means that this verification game is actually never played. But it has to be there, and it has to be in code and correct for this whole mechanism to work. Yeah, so if there's someone who watches, then the verification game will not be played, but still everything works out. But the problem is, so everything works perfectly. All people, nobody cheats. Everything works fine. There's one honest verifier who verifies everything, but so. How the game works is that, of course, this is all deposit based, so all participants put a deposit on chain, and if they are guilty of cheating, then their deposit is destroyed, and the people who discover that fact, they get a reward. So the verifier will get a reward if they find an error. But if everything works fine, then yeah, they never find an error, so they will never get a reward. And this is actually a very fundamental problem, because how do you, as a verifier, how do you prove to a system that you check the computation? You can at the end you can say, oh yes, yeah, 7. That's also the result I got. But yeah, I mean, you knew the result beforehand, so how can you? Yeah, you can just have copied that. So yeah, over time the verifier will lose interest because they are not paid in any way, but have to do exactly the same work as the main problem solvers. So they will stop looking, and as soon as the solvers notice that no one is looking anymore, then they can cheat and the whole system breaks down. So we need a way to pay verifiers for their work. And the solution to that is something called forced errors. And the way it works is you basically inject an error into this whole process, which can then be detected by the verifiers, and then they can be paid for that. So,
who pays them?
the system. So,
Just its name.
huh?
System.
No, so, okay, perhaps I should have explained the whole setting a bit more. Sorry about that. So, if you want the TrueBit system to solve a task for you, you have to pay for that. So you have to pay, yeah, a fee. And this fee is in part paid out to the person who posts the solution to the task, and in part it is saved in an account we call Jackpot. And if such a forced error occurs and a verifier finds the error, then the verifier is paid from that jackpot. And so, yeah, I mean, of course, it's a bit different. The solver cannot be punished because the solver had to inject this forced error. It's a pseudo-random but deterministic process, and the solver cannot choose to include or not include it. Okay, is that clear how that works?
So genius.
Wait for it. No, because yeah, it has flaws.
What do you must run in?
So true randomness does not exist on the blockchain. That's why we need pseudo randomness, and it's kind of there are multiple factors that go in and it's just a process that can be verified by a smart contract. So the
What is it exploitable?
in which way? Yeah.
So that who injects the error? Is it the proposer himself? And
So the solver. So
yeah.
yeah. So there's the proposer who gives the tasks,
Oh,
then the
yeah,
solver who
so-
solves the tasks and posts the solution on the
how
blockchain.
does the solver know that he has to include an
So it's some deterministic function taking into account, I think, the block hash and perhaps also the hash of the solution. So the idea is that the solver knows that this just happened. Okay, let's perhaps skip to the next slide where we will find another problem. So the solver knows that this happened. So the solver is forced to inject a forced error, and this condition is also verifiable by smart contracts on chain. And if the solver does not inject the error, then he or she will be punished. And the problem is now, so everyone who detects this error gets a reward. And now the solver can, of course, notify verifiers about the fact that the forced error just happened. So the ideal world, the solver injects the error but does not tell anyone about that, because we want the verifiers to actually re-execute everything. So, right? So, okay, perhaps, these forced errors, so the rewards for finding the forced errors are of course not for the forced errors. We pay the verifiers rewards at forced errors because that's where we can pay them, but the actual idea is that we want the verifiers to verify all other transactions too. It's just, so they have to verify everything because such a forced error might happen in every single task. And you only know that it happened after the fact, basically. And so as a verifier, you have to acquire that information that a forced error happened, and the way we want the verifier to acquire that information is by just re-executing the task. Okay? And there's a second way that they can acquire this information, and that's by asking the solver. Right? Because the solver knows that the error happened because they had to inject the error. And of course, on a smart contract blockchain, you have all sorts of weird bribery things which are possible. So it's quite trivial to just add a mechanism where solvers are paid by verifiers to tell them this, to give them this information. And the question is, how do we?
So basically, the verifier is only paid out when that is an error, but not when he verifies that correct computation.
Sorry, can you say that?
The verifier is a payout, but he catches a computation that has an error.
Yes.
But,
So this.
but not when the original computation is correct. The verifier verifies that the computation is correct.
Yeah, you can't, as a verifier, there's no way to prove that you re-ran the
So the verifier only gets the payout when there is
Yes,
error.
so it happens at random, more or less regular intervals.
Yeah, so the random error is the way for the verifier to get payout.
Yes,
And the
yes.
mining.
It's like the
Yeah, exactly. It can be compared to mining, where you get a payout, not with every block, but at certain points in time.
Which then shifts the motivation more, which is maybe his question, towards solving those injected errors. So the people are then more motivated to check those actually, and it might decrease their motivation to do other.
Sure. So
Even if they don't know yet, but might they find a way?
as a verifier, since you can only pay for forced errors or for errors, you want to only verify these tasks, but there's no way to find out whether it. So I mean, the only way to find out is, or there are two ways to find that out, and one is rerunning the computation, and the other is getting that information from the solver.
Yeah. Yeah. Wouldn't the other way around be to randomly pay people for checking the verifications, even though you can't prove if they really did it?
So whoever, we don't care who actually runs the verification, as long as someone does.
It's like a search dog. You have to put in fake rewards to keep them interested.
Yeah, but I just question whether it increased it. I mean, like it increased the interest, but maybe for the wrong motivation. So you want. I just ask myself, it's also possible to increase the motivation for the things where you say you can't check whether they really.
You have to run everything to find the rewards, the errors, forced errors.
I mean, it's exactly the same thing you do, whether you just verify. Okay. So, yeah, how do we prevent the solver from telling the verifiers that yeah, okay?
Maybe randomly choosing the verifier.
Sampling.
Huh?
So that would be kind of like a full sample. Determine how much information you need to validate that this is a true outcome or true computation, and so some random sampling.
Yeah, I mean, so on a blockchain you never know. On a blockchain nobody knows that you're a fringe. So you don't have a reputation system attached to the solvers, and yeah, it's difficult. And also, I mean, so we want this to be tight also against kind of arbitrary bribery smart contracts, and that's why just sampling the solvers is not the best solution, I think. But you're randomly changing the, what did you say, randomly changing the solvers?
Yeah, no, not the solver, the verifier. Basically it has the same randomizer that puts the guys who put the errors in, of course, errors, making the same for verification.
So something I perhaps didn't say clearly is that anyone can be a verifier, and also you can you can step in as and challenging a computation from outside at any time. And you're not, so that's another model when you say you have to verify the computation, but if you do that, then you have to punish people when they do not verify the computation. That's kind of a tricky thing to do. Okay, but that's what we came up with as a solution.
But listen, one question. So basically, every time I do a computation, I do have to submit a request on the blockchain, and the solver has to submit the result. So that's basically for each computation, no matter how large it is, two transactions.
So this is meant for large computations, yes, and the whole process takes multiple transactions, yes.
Okay, so it's not scaling the amount of computational transactions, it scales the size of the transaction.
So it takes a constant amount of transactions in the good case, where we don't have to run the verification game, but the length of the computation can be
increased compared to what we had earlier on the blockchain. But the thing, I cannot do more transactions, right? I can only do larger ones.
Yes, so TrueBit does not scale the number of transactions, it scales the amount of computation in transactions.
But it feels like with a bit of a tweak, right? We just bundle transactions together.
You could, yeah.
Okay, this is how you prevent the solver from sharing the information about the forced error with the verifiers. And so we don't prevent the solver from also challenging their own computation in case of forced error. That's a good thing. So it's just the solver just get another reward, and we can factor that in with the regular rewards. So that's fine. But the idea is that the reward will decrease dramatically the more challenges there are. So these numbers can actually be improved, but that's how it is written in the white paper. So I will explain it like that. So if we only have one challenge, this is usually just the solver challenging him or herself. The solver will get a reward of 100. That's just some fixed number. And if there's another challenge, then the two challenges will both get 25, and in sum 50. So if the solver shares that information with someone, the solver's reward will decrease from 100 to 25. So that's not something you would like to do. And also, if you are a verifier and acquired that information by rerunning the computation yourself, you also don't want to share it. Because then, yeah, if only you and the solver found that out, then your reward decreases from 25 to 8.3. So, yeah, that's the way how you can solve this information sharing problem.
Okay, this basically stands against whatever the computation is worth, right? So if the computation moves a lot of money, it might be, or like could potentially move a lot of money.
So of course, yeah, this all runs on a blockchain, and even the blockchain has an upper limit of how much, what do you want to do on the blockchain, which value is attached to what you do. So if you put something on a blockchain which is worth more than the whole blockchain, then an attacker can just attack the blockchain and get this thing somehow. Yeah.
Two questions. First, the first one is not really so it's connected, but it is not a problem for this for the solution, but it's another attack. And can I as a verifier not simply wait until someone challenges and then only run this particular computation, because I'm quite sure that there's a problem in this particular computation, and then get all the rewards without verifying other?
Yes, very good question. That's especially relevant for the solver, because the solver immediately knows there's a forced error, so you could just watch if the solver challenges or not. And because of that, you have to randomly make something called fake challenges. So it has to be some commit reveal mechanism where you first post something to the blockchain which looks like a challenge, but then in the end turns out it's not a challenge.
But then, so that solves that. But another problem which I see, for example, just some random numbers. If you have like a forced error every 10 computations or whatever, and each computation requires quite a lot of work for the solver, and so what he really would like to do is just post fake results, and he earns a lot of money because he doesn't have to have his computing cluster run or whatever. And so what he could still do would say, okay, I just share this information anyways, and for these forced errors I don't get any money because I share the information and everyone can challenge and so on. So I don't get any money for the forced errors, but I save all this money for the other transactions where I don't have to run my computing cluster. And because I always share the information about the forced error, no one will ever look at my other computations, because they know if I didn't share information about the forced error, there won't be an error. So no one will challenge any of my other computations, and I'm like, so if there's a mismatch between money you can earn on the forced errors and money you can save by not having to run the other computations.
So this is the reward the verifiers get. So if you do it every 10 tasks, we were more thinking about every 100 tasks. But so this is the only reward the verifiers get for verifying all the transactions, all the tasks until the last forced error. And the amount of work they put in is the same amount of work that the solver puts in. So the amount that is paid out here is extremely large. So it's comparable to the sum of all the computation fees paid for the tasks until the last process. Okay.
You're talking about running arbitrary code, right? Like running some light plant, maybe running some Eiffel software or something, some crazy thing. And but then at the same time, you gave a couple examples where there was the need for on-chain computation for injecting the error, as well as for the computation of the last step between the right result and the wrong result in the workflow. So, but wouldn't that require that the on-chain computation has to be running like Eiffel code or Python code or something?
So we're planning to implement this single-step verification for a process for an architecture called Lanai, which is developed by Google for some networking processor. And this architecture is quite simple, and Google wrote an LLVM backend for that architecture. So you can compile C, C++, and Rust code into that backend. And I'm not sure what Eiffel is written.
Eiffel is a language from the 90s. I was just being arbitrary, random. So.
Yeah, but so yeah, anything you can where you have. So if you have a if you have something that runs on LLVM, then you can do it. And even if you have an interpreter written in C or C++, then you can also do it.
How about having access to things like I have access to Solidity, like block number and block hash and value? Like I don't have to do these kind of complicated, right?
Yeah, I mean it's not part of a block, so it doesn't really make a lot of sense. And it's just so also this binary search that only works for pure functions. So you have to include the full state in input and output. So you can work on swarm files, as I said, but that requires that you actually have a proof that the file is available, which is possible in Swarm, at least in the final version. And that's why you basically put the hash of the Swarm file as an input, and then you can read it during the process.
But I don't have any state, and I cannot do any value transfer.
So if you want to use state, it has to be part of the input. But it's fine. I mean, yeah. So you can take the whole blockchain as input and run a single block on that. Yeah.
Are there always multiple solvers for every computation, or is one solver sufficient?
So, yeah, this is something that we still have to work out in experiments, but it depends on the reliability, but perhaps one or two. Sure.
Is there a strategy to wait what another solver, a competing solver, gets as a result and resubmitting the same result? Is that a possible strategy to cheat the system?
Okay, sorry, no, yeah. It only works with, so this model we're currently planning only works if there's one solver. So you post a task, and then the solver commits to the task, runs the task, and posts the solution. And the others are verifiers, basically, but do the same job.
How if one, you said that the challenge, when you said that there are two solutions, and then there's this binary search going on, comparing the two solutions. How is this done when there's only one solver and one solution?
I know there's a solver and a verifier who are in disagreement.
Okay.
That's how it is. Back there was a question, or?
Yeah, when did you release the white paper explaining this?
Sorry, what?
When did you release the white paper?
Did 2 weeks ago, I guess. Or
Right, that's why I have it.
it's a technical white paper, I have to admit.
Yeah, it might be better if just read the white paper and then ask you this question. But another attack that I would come up with. In principle, you would have a situation where then there would be a solver and there would always be verifiers. That's what we want. And so, in the end, every time there's a false error, there won't be the only one challenge because the solver will challenge, and I don't know, 1, 2, 3, 4, 5, 6 verifiers will challenge. And at some point, you will reach an equilibrium because if there are too many verifiers, no, they won't earn anything, and if this number decreases, then they won't, the earnings increase until there's some kind of equilibrium. And let's say this equilibrium is the solver plus 3 verifiers, just for argument's sake. wouldn't it then make sense for the solver to just create 4 accounts and always submit 4 his challenge and 3 other challenges, so everyone looking at that sees, there are already enough verifiers, it doesn't make sense for me to join in, and then same problem as before?
Yeah, that's called the scaring of verifiers attack. And, so, yeah, there is a solution to that, and the idea is that you always have multiple parallel tasks, and verifiers choose randomly between these tasks. So it's a bit difficult, but it's explained in the white paper. Yeah.
By the way, I really like this. It's really cool. What is the roadmap overall? Where are you guys?
No, it doesn't show the roadmap. So, yes, we don't have a full roadmap yet, but we're actually planning on implementing that, and we're looking for both funding and developers to do that. The exact specifics are not clear yet, but yeah. To wrap up, so yeah, I explained how TrueBit scales trusted computation with unanimous consensus. So, and the only requirement is a working, trusted execution environment with limited capacity, so a blockchain. And it can be scaled to more or less unlimited capacity and with unanimous consensus. The website is TrueBit.io, and the technical white paper has a complicated link, which can also be found on the website. Okay, thank you.
Can I ask one more question?
Okay.
In terms of scalability, like, is that an either-or scenario, or can you have this, like TrueBit, run simultaneously as the other proposed solutions?
Yeah, it doesn't require a hard fork. It's just another smart contract on Ethereum.
Okay.
And it also, so the whole system does not require Ethereum specifically, but just some smart contract blockchain system, some trusted execution environment. One more question? Or? Okay, then.